So far in this course, we've spoken only of contact modes, a constant height mode when there's no feedback loop, or constant force mode when there is. The reason for that is we wanted to have something simple to talk about just to get you started practicing with an AFM. But there are limitations to contact modes. There could be high enough tip sample pressure to cause damage, either to the tip or the sample. You could displace weakly bound absorbates. So imagine a substrate like this, a carbon nanotube like this. The tip comes along and you'd like it to go up and over the carbon nanotube, continue on its way after registering that the carbon nanotube is there. But if there's not good adhesion between the nanotube and the substrate, then the tip just rotates the nanotube and continues on along its merry way without going up and over it. And so therefore you never see that it is there. Disturbance of viscous samples. Think of spreading your peanut butter on your bread and then rastering your finger back and forth through it. You leave a little trail with your finger, and you're not getting a good representation of the surface. And finally, if your tip or your sample must remain absolutely clean, you don't want any contact at all between the tip and the sample. So what can you do? You can oscillate the cantilever, and that's done by means of placing a piezoelectric element at the base of the cantilever. The photodiode records those oscillations, and now we need a new circuit element. We need a lock-in amplifier, and what that does is it locks in on the frequency that is being used to drive the cantilever and determines the amplitude of oscillation at that frequency. It then sends a signal to the feedback circuit that is proportional to that amplitude. Then the feedback loop uses that as the feedback, the set point parameter. And so you still get an image that is Z position of the scanner as a function of its X and Y position. But now that is a result of the feedback loop holding the amplitude of the cantilever constant rather than its quasi-static deflection. In order to understand the dynamic AFM behavior, we need to talk about resonance. So let's imagine that we have a mass hanging from a spring, which in turn is attached to a support, and we may control the position of that support vertically. If we're operating that at a very low frequency, then the movement of the mass matches that of the support. If we go up to the resonant frequency for the same excitation, we get a very large response. The resonant frequency is this expression here, F0. It's equal to the resonant frequency in radial units divided by 2 pi, or 1 over 2 pi root of spring constant divided by the mass. If we continue on up and go to a high frequency, well above the resonance, then we get a small amplitude again. In fact, it could be very small. If we plot that, the response, I'm going to call it amplitude over A0, where these three things here are the excitation amplitude of A0, then at low frequency, here this is equal to 1, and then we go up to the resonant frequency and then we drop right off. So we have here is F0, and the region up to the right, this is what I was indicating by a very small response at high frequencies. I'm going to show you a video of a mass oscillating on a spring. That represents our cantilever. Embedded in that mass is a magnet, and we're going to bring a two-pole magnet near it to interact with it both repulsively and attractively. This will represent surface forces between the tip and the sample. Here's the mass oscillating by itself, no outside influence. Now look, repulsive, and now attractive. Attractive is definitely slower frequency, and repulsive was slightly faster. We can represent this behavior on a plot of normalized amplitude as a function of normalized frequency. The normalization just means that we don't have to worry about specific values for these numbers. What's important is how the peak shifts depending on what kind of force is acting between the tip and the sample. Attractive forces make that frequency of oscillations lower, repulsive forces higher. When you sit down to a dynamic AFM session, first thing you'll do is make a plot like this one on the right, amplitude as a function of frequency, for a free cantilever, so you would get the black line. The next thing you would do is choose a drive frequency and drive amplitude. Let's take a drive frequency on the left-hand side of the black peak. Let's take this frequency here. Note that that frequency corresponds to a higher amplitude for the attractive peak and a lower amplitude for the repulsive peak. If we were to choose a drive frequency on the right side of the free peak, you might choose a frequency like this. And note that we've got an inversion now. The amplitude for the repulsive peak would be higher than that for the attractive peak. So what happens is not only do you set a drive frequency, you set a set point amplitude. That's the amplitude that the feedback loop is trying to keep constant. Normally that's indicated by a percentage from the top of the free amplitude peak. So let's say I chose this level here. That looks like it might be 70-75% of the free amplitude. Note that if you have chosen a drive frequency lower than the free resonance, that corresponds to repulsive interaction, and higher than the resonance corresponds to an attractive interaction. So your choice of drive frequency will determine whether the tip nominally stays out of contact with the sample or smashes into the sample at the end of every oscillation cycle. So you might have heard these terms about AFM: non-contact mode and intermittent contact mode, abbreviated IC AFM and NC AFM. Another thing you should be aware of is the idea of phase. Here I have sketched a cosine wave in gray and a sine wave in white as a function of time. And you see the equations down at the bottom. What's missing is the value of theta in the second equation. And what theta represents is how far behind the sine wave is from the cosine wave. So if you remember your trig, this value is pi over 2, but since it's behind it in time, the value of theta is minus pi over 2. Let's return to our amplitude frequency plot. And now I've added a secondary axis on the right for the phase angle. Zero phase means the excitation and response are moving in the same direction at the same time. Minus pi, out of phase, means that excitation and response are moving in opposite directions. Minus pi, you could also write minus 180 degrees. So at low frequencies, oscillators are in phase. They go through a dramatic change around resonance, and then they become out of phase at high frequencies. Returning now to our plot of amplitude and frequency, let's put phase on here. And I'll put phase on for the red curve, the repulsive curve. And if we remember, that goes from 0 to minus pi. And if we say our derived frequency is about here, with our set point amplitude about there, and now we're imaging and we move to another part of the sample, let's say that part of the sample is very stiff, and we might have a interaction that looks very strange, like this, and its phase would also be very different. Might be cut off more like that. Then as the feedback loop is keeping the set point amplitude and the drive frequency doesn't change, then what's happening is that the phase goes from this value to this value. So we can separately make an image of the phase while the set point amplitude is remaining the same, and this is called phase imaging. And it's used quite a bit because there's can be some very good contrast in phase images because of the steepness of change of the phase angle near resonance. I started this lesson with a list of limitations of contact AFM. It's only fair to end with a list of limitations of dynamic AFM. That lock-in amplifier is an extra circuit element in the feedback loop. That means the whole loop responds more slowly. Depending on the amplitude of the cantilever, you're going in and out of a range of surface forces that can be hard to interpret. Because it's a resonant technique, the data are very sensitive to data acquisition parameters, so be careful to use exactly the same parameters if you need to compare samples. And if the cantilever is weak, there can be sudden jumps as you move from spot to spot. And that's fairly complicated and best left for an advanced lesson someday.